Hello. Is it working?
Mic is only for recording. You'll have to use this.
Okay. Hello, hello, hello. I'm audible at the back? Loud and clear? Awesome. Coffee, guys? Coffee. Okay. Anyways, we'll get started. Right on time. Yeah. Cool. So today, what we are going to talk about is infra to power code level semantic search. Too many fancy keywords here. Infra, semantic search, code level. We'll go into that. We'll probably talk about what keyword search is, what semantic search is. Too many things are there. We'll deep dive into it, but we have 20-25 minutes, half an hour, so we won't be talk in depth about it, but I'll try to cover as much as I can, right? It's a very vast topic. But I'll first start with my introduction. My name is Sanchit, and I work at Atlassian as a senior software engineer. Been with Atlassian for the last 3.5 years now. Apart from that, I work as an instructor also. I teach the GenAI cohort at AirTribe. Over the past, I have worked with 2 companies. I was an SD at Amazon and an SD at American Express. My friends say that all my companies' names start with A, so my next company is probably Apple. That's what they say. But anyways, I also used to teach full stack development at Scaler. Over the last 2-3 years, I have helped around 500 learners to learn some new skills, be it in full stack web development or GenAI now. Over the last 2 years, I've been working with GenAI, ML, AI systems. I create backend for those. Let's get started. That's a brief intro about me. Cool. So the theme is coding agents and AI, right? The other Sanchit also talked about that. So I'll build upon that. So coding agents, right? We all know what coding agent is. Some people use it for vibe coding. Some people use it for sparring, architecture, writing the actual code and whatnot, right? And we have used so many coding agents in the past. For example, the most common one, I hope everyone remembers what this is, right? Cursor. So you have this intelligent IDE wherein you can give it some prompt, it will generate the code for you, it will plan everything for you and whatnot. Other coding agents are also there. Copilot, which Sanchit was talking about, and some other ones, maybe some less popular ones. So this is AMP, another coding agent that we have. And do we know what this is? Now, this is Rovo. It's Atlassian's AI agent, so a shameless plugin here. Sorry for that. Cool. So what is the job of a coding agent? Right? The job of a coding agent is very simple. The job of a coding agent is figure out what to do. You give it a query, right? The first thing is it needs to figure out that what needs to be done. And the second thing is just do stuff, right? Essentially 2 things, figuring out what to do and do stuff. Now, what qualities do we see in the final output that is generated by these coding agents, right? So on what factors the quality of the work depends on? It's very simple. The quality of work depends on the quality of context that you give to these agents, right? And the capability of the underlying LLM. If the underlying LLM is very powerful, but you are not giving enough context, it will suck, right? If you're giving very good context to the underlying LLM, but the underlying LLM is not even powerful, it's not very capable, it won't be able to do the good job, right? Now, we are not going to talk about the capabilities of the underlying LLM. We are trying to focus on the quality of the context, that how can we provide better context via these coding agents to the underlying LLM so that they can work efficiently, right? So before talking about that, how can we give a good quality context to these LLMs, it's important to understand that what a good quality context is, right? Majorly 2 things, right? We'll keep it very simple. It has to be crisp, right? Big context is not always a good context, right? If you provide 200K tokens for a very simple task, your LLM will confuse, you will burn more money, it will take more time, the output won't be that good. right? It has to be very, very crisp. The shorter the better, the more accurate the better. So if you are able to provide more crisp and accurate context to these coding agents, the underlying LLM will perform a good job and you'll get a better answer, right? Now, the next question is, we know how to provide, what a good context is. The next question is, how can we gather a good context, right? For example, you go to any coding agent. You go to a Cursor, you go to Copilot, you go to AMP, Atlassian Rovo, whatever, right? You share a query. You have a code base. You'll share a query that, hey, how to add an auth header in a request. That code might have 100, 200, 500 files. In some file, you may have written the code for an HTTP client. That HTTP client might be making some REST request to some backend service, right? The requirement is you want to add some additional headers in that particular request. So how you do that? You go to a coding agent, you ask it that, hey, how to add the auth headers in request. So what is the basic way to do it, right? May not be the very optimal way. What is the basic way to do? How we used to do it before. We used to extract keywords from the user query. The LLM will see that, okay, I have a query. Let me extract out some essential keywords from this query. So the LLM will see that, okay, the client will see that, okay, I'm talking about auth. I'm probably talking about headers. I have something to do with the request and have to do some additional to those requests, right? So what it will do, it will extract out these keywords. The next thing that your coding agent will do is try to find similar keywords that are there in the query, right? So for auth, it can have authorization or authorize, right? For request, you can have a request, client, or token, or these sort of keywords, right? It's trying to expand its keyword domain, the keywords that it wants to search. And then the next thing that the coding agent will do, it will search all the files which may have these keywords in the code or have these keywords in the name, right? So essentially, what we are doing here is we are extracting out the keywords. We are making guesses that, these keywords might also be related to the query that the user is asking. And then I'm doing a normal search. If I have 500 files, the search might take a few milliseconds, right? But if you have, imagine you have 50,000 files or 1 lakh files or even 5 lakh files in a code basis, right? You're working on a big monolith. Then this approach will suck. It won't give you the better output. Why? It will take 3, 4, 5, even 10 seconds to scan such big code bases, right? And as we can see, all it's doing is it's doing some guesswork, right? So the problem with semantic, so this kind of search is called a keyword search. So because what we essentially are doing is we are picking out some keywords and then we are searching those keywords across my code base. This type of search is called keyword search. So the problem with keyword search, the keyword search misses the semantic meaning. So semantics is very important here, right? Because what we are doing is I asked about auth, right? But there could be one file which is actually working on auth, but it may not have those keywords in it. So my agent will miss those files. Why? Because it's not even aware that, in those files I'm doing something related to auth just because those keywords are not there. But that can very well be the case, right? Not every client related file or REST related file will have these sort of keywords. So I'm not focusing on the meaning, the semantics of what I'm actually trying to do in the code, but I'm only relying on certain keywords. And that's a missing part. The next thing, high token usage. So what my agent is doing here is, my agent is essentially randomly reading files, reading the content of the files and those kind of stuff, right? It's making guesswork. It will take higher time, slow exploration, because my agent does not know where to look for, right? It will take a longer time, and it has to read probably 10 different files which are garbage for it, right? And they are not very relevant for it. It will burn more tokens. And at the end, everything boils down to how many tokens that you are using in terms of the cost of your coding agent. The higher token you use, the more money it will cost. And again, poor scalability, because as I said, it may work for a code base which has like 500 files, but it might not work for a code base which has 5 lakh files. So these are certain problems with the keyword search. What are the solutions for that? Solutions are simple, right? Simple as in that the first problem is I'm missing the essence of the user query. I'm not understanding that what the user is actually trying to say. The important part here is to capture the essence of the user query. Another piece is retrieving the relevant code. So instead of doing just guesswork, if I can pinpoint to the exact files where that code is written, that will help me. That will bring down my token burn, and that will increase the speed of my agent, right? It will perform more efficiently. The solution is simple. Just capture the essence of the user query and retrieve the relevant code faster, right? Fast is very important. I mean, if you write a query and that query takes 10 seconds or 15 seconds, the agent takes 10 seconds to come up with the first reply, you will probably move ahead to some other agent, right? No one likes slow softwares. So now we know what the problem is. Now we know what the solution can be. The next thing that should come in our mind is how can we implement this solution, right? So what probably we can do is, for example, let's try to see that how can we actually capture the essence of my code base, not just the keyword, not just the file names, but the actual essence, the meaning of my keyword, that what I'm actually trying to do in those code files. For example, you have certain artifact, right? In our case, we are talking about coding agent. So let's say the artifact is the code repository that you have. What we'll do, the whole big repo won't carry a single meaning, right? There would be a certain module which will focus on one thing, another module which will focus on some other thing. The meaning of module 1 will be different from the meaning of module 2, right? And not even at the module level. A module can have 100 different files. Those 100 different files might be doing 100 different things. And those 100 different files doing 100 different things might carry 100 different meanings, right? So what we do, the first step is we use something called a chunker, right? As the name suggests, it takes an artifact, a coding file or a coding repo in this example, and we chunk that particular file, right? We chunk that whole repo. We might chunk at module level, we might chunk at file level, we might also do some sort of intelligent chunking, right? Even at the file level, there can be 10 different functions. 2 functions might be doing one thing, 3 functions might be doing a similar thing, right? A similar use case. So we'll do some sort of intelligent chunking, and we'll create chunks, and one chunk will carry one meaning, right? That, okay, this chunk is rendering the UI. This chunk is rendering my banner in my UI page. This chunk is handling my authentication part. This chunk is actually talking to the backend service. So we pass our artifact, our code repository to a chunker, and that gives me, obviously, chunks, right? These chunks are a smaller part of code, and each chunk is doing one specific thing, right? So we are able to break down the whole repo into smaller pieces, and one piece do exactly one thing. The next thing is, how do you define that thing, right? What it is actually doing. So for that, we have something called embedding models, right? Embeddings, very fancy word. If you're working with in the AI ML domain, so that's a very fancy word nowadays, embeddings. So what embedding is? Embedding is something which helps us to capture the meaning of something, right? For example, I mean, there can be an image, right? That image of a sunset, right? If you create embeddings of that image of a sunset, those embeddings will have certain values that will carry the meaning of that image, right? For example, there can be one pillar in that embedding which talks about, okay, how much orange component is there, right? In a sunset, it's highly likely that there would be more orange. So it will score it higher, right? So similarly, we define thousands of pillars across which I give these scores to these pillars, right? To give you a context, embeddings is nothing but a fancy list, a long list of floating point numbers. And these floating point numbers are essentially scores on the scale of -1 to 1, right? 1 being higher, -1 being lower. So for every chunk, we define these 1,000 different pillars, and for every pillar, for every chunk, we define some scores, that how good or how bad, how relevant or how not relevant that particular chunk is for that particular pillar. So we create embeddings, right? To create these embeddings, there are specialized model, and we call them embedding models. The different AI providers provide these embedding models. You have one from OpenAI, you have one from Claude, there are some open source models as well. So any model will work. So when you pass these chunks in these embedding models, you'll get embeddings, right? Embeddings are nothing but, again, a long list of floating point numbers which captures the essence of that artifact or that particular chunk, right? Then the next thing is we need to store these embeddings somewhere in order to retrieve it, right? Typical databases will not work. I mean, in typical databases, what do you have? You have, if you are using a relational database, right, you have typical tabular structure in which you store textual content, JSON content, numbers, strings, and whatnot. But these are embeddings, right? Typical, normal, classical data structures don't serve very well for these kind of data. So that's why we have created a specialized database, which are experts trained in storing these embeddings and retrieving these embeddings. And we call these databases vector databases. You might have heard of it. There are a lot of vector databases in the market. Some are free, some are open source, some are paid. Some examples are, I mean, there's ChromaDB, again, open source. There's Quadrant, open source. More traditional databases like Postgres also offer a functionality which you can use to store these embeddings, right? So a vector DB functionality is also there in Postgres as well. So what we do, we have an artifact, a GitHub repository with, let's say, 100,000 files. We pass those files to a chunker. The chunker creates chunks. Each chunks carry a small part of the code which is doing one specific thing. Then we pass those chunks one at a time to these embedding models. These embedding models, we create embeddings. Embeddings are nothing but a long list of floating point numbers who actually carry the meaning of that chunk, and then we store them in the vector database. So in this way, we are actually capturing the essence of my code base, that okay, this particular file is talking about authentication. It might not have auth related keywords in that file name or auth related keywords in the code base, but it's actually capturing the meaning. Now, next thing, we have captured the essence of my code base. So what's the next step? The next step is, how will you do the matching? How will you retrieve the relevant chunks? So for example, a user query will come. The query can be that, hey, how can I add an auth headers to my request? That query will come. The next step would be to pass that query to the same embedding model and create embeddings for that particular query, right? Now we have embeddings for the query, and now we have the embeddings of the whole code base that I used to have, right? Now what I need to do, I need to do some sort of matching, right? That the embeddings of my query, which are the most matching code bases snippets where the embedding matching is maximum, right? So embeddings are nothing but vectors. I'm sure everyone must have studied about vectors, probably in their 11th standard, 12th standard math classes, right? So vectors. So embeddings are nothing but vectors. They are represented by a long list of floating numbers. So now what we have a vector for the user query. We have 100,000 vectors which represents my code bases. Now all I have to do is I need to see that which vector out of those 100,000 vector files for my code lies closest to the vector for my user query, right? The closer the vector is, the more relevant it is for that particular query, right? So for example, a vector for a dog and a puppy will lie similar in a plane, but a vector for, let's say, a dog and an airplane will lie very different in a vector plane. So if I can somehow figure out that, okay, what is the distance between the two vectors, I can get the closest vector, and those closest vector will be the closest things which are to my query, right? And we talked about vector databases. So vector databases not only store these vectors, store these embeddings, they also give you a capability to the similarity search. So what is a similarity search? So what we do in typical databases, you have these where clauses, right? That where x equals y or a is greater than b, these kind of searches, right? So we use equals to a, equals to, greater than, less than, these kind of operations. But that is structured data. For vector database, what we do similarity search. So the vector databases give me a similarity search feature as well, that I give an embedding for a query, right? And I ask my vector DB that, hey, which are the vectors that are closest to the query that I'm sharing with you, right? So my vector DB will perform a similarity search. There are so many ways to do similarity search. I mean, that would be the topic probably for another talk, but they do the similarity search and they give you, for example, top 10 chunks whose embeddings are closest to the embedding of your query. That guarantees you that those 10 chunks are mostly correlated to the query that the user is trying to ask, right? You'll get the relevant chunks from the vector databases, and then you can pass those specific chunks in the context to your LLM. The benefits, again, you're not spending much time doing the guesswork. You're not relying on the keywords, but you're actually relying on the essence of these code bases, right? So you reduce the guesswork, you reduce the time in which it spends to find the relevant context. You're providing more concrete context to the LLM, right? Again, wins in all domain. So what we typically create the embeddings of all my code bases, right? But the next challenge that comes is how will you keep these embeddings fresh? For example, I take a cut from my code base, right? And I create the embeddings and store it in my vector database. But the code base is evolving. Every day, new PRs are getting merged. How will you make sure that the embeddings that you are storing in your vector database, they are the relevant one, right? They are the fresh ones. And that's the problem. How can we keep embeddings fresh? For example, you are using any source management tool. Again, shameless plugin, we are using Bitbucket, right? We have webhooks on these kind of softwares, right? That, hey, just whenever, every time a PR is merged, just send me a request, right? I hope everyone is aware of what a webhook is. So essentially, you get a request from the server itself that some sort of event has happened. So you can create a webhook listener. That listener will get a request from Bitbucket that every time a PR is merged. What we'll do, from that request, right, I'll extract out that, okay, a PR is merged, tell me which file has changed, what code I have added, what code I have removed from that particular PR. I'll get a code change and I'll do the same exercise again. I'll pass that code change into a chunker. The chunker will create chunks and those chunks will be passed to, again, the same embedding model, and the embedding model will create the embeddings. So these are the new embeddings of the new code, right? And then what we need to do is, we need to do an upsert operation in my vector DB, right? Upsert, I hope everyone knows what an upsert is. If a new code is added, so new embeddings will be created. So in that case, I need to insert those embeddings in my vector database. If I have modified some previous code, then I need to update the embeddings for that particular code base in my vector database. So once that is done, my vector database will have the refreshed query, refreshed embeddings, right? In near real time. And again, the improvements, keyword search, the older way to do it versus semantic search. So precision, you get low precision in a keyword search, but a higher precision in semantic search because you know exactly which files to pick to provide that particular context, right? So precision is high. Time, again, keyword search has to do a lot of guesswork. They'll have to read probably 10x more files which are not even relevant for that query. So it will spend more time, but versus semantic search, they know exactly which chunk to pick, right? So they will be spending much less time collecting the context. Next is tool calls. Tool calls as in the operations that my coding agent performs, right? So in terms of a keyword search, it would be high. Why? Because it would do 10 tool calls for a read file, 10 tool calls for open files or whatnot. It's doing the guesswork. But for semantic search, you'll have only one tool call that, hey, a semantic search tool call. Just go to your vector database. This is my query. Give me the most relevant code. And last, token one, obviously. We are bringing down the tool calls. We are reading less code. We are passing less code in the context, but better code in the context. So that will bring down the token burn versus, what we have in semantic search, keyword search versus what we have in semantic search. To give you one example, for example, I have this code base. Okay. Better? Okay. I have this code base, right? It's a normal web application, a React application, wherein I'm using some APIs to give me some movie details, right? It's a normal web application. So I want to know that, hey, One second. That which API are you using to get the movies data? For example, you are getting onboarded to this new project, right? You don't want to go ahead and read all the files. You simply go to a coding agent, you ask that, okay, which APIs are you using to get the actual data, right? So what it does is, see, it will try to first see that which all files are there in your code base, right? It will analyze all the files. If I expand this, it's reading different folders. So it expanded the whole code file, the code repo. Then it analyzed the source project. It sees that, okay, I might get something in the source project. So let me just go to the source project. So it might have read 10 different folders unnecessarily, right? Because later it realized that the good quality files would be in the source folder. So again, a wasted tool call. Then what did it see? It is making a guesswork. It is making a guesswork that, okay, probably search for API keyword, fetch keyword, Axios keyword, and these sort of keywords. So it's doing the guesswork. It did not find any results. So then again, it makes a lot of guesswork, it reading different file, it does not know what to do, right? After a lot of exploration, we can see there are what, 5, 6, 7, 8 different tool calls, wasted tool calls. So after that, it realized that, okay, probably these are the files and these are the files that it is actually using to make the call to the backend, and then it reads that particular file and came up with an answer that, hey, this is the API that you are using. This is the final answer. This is the final answer. It is able to give me the final answer, but it gave 10 unnecessary tool calls. It spent a lot of time to give me that answer, right? In the next query, what I asked it that, hey, can you use the semantic search tool call for this query? Don't use keyword search. Don't make guessworks. Give me the exact answer. So see what it did. So it thought for 2 seconds that, okay, the user is asking me to do a semantic search. So let me do a semantic search. I do have a semantic search tool with me, right? So it's exploring the search space and it searched for this. This is the exact query that it fired to my vector database that, okay, this is my query, give me the relevant code files. It's not exploring irrelevant code files, it's not reading unnecessary code, it fired a query to the vector database. The vector database must have returned the exact chunks wherein I'm calling some backend API, right? So if I scroll down, you see, you get the exact code chunks where you are actually calling the backend APIs, right? So this chunk stores the meaning that we are calling the backend API, and it actually gave you the code base. So it will only give these 2 files, these small snippets to the backend to actually give you the final answer, right? We can see the improvements. We are not taking 10 different tool calls, just one tool calls. And the output is also very relevant. I got the exact chunk which I need, right, for that particular query. This is how a semantic search can improve the quality of your answer, the quality of your search, right? Brings down your tool call, improve your speed, bring down your token burn, and increase your precision, right? I hope that makes sense. And that would be all. If anyone wants to connect on LinkedIn, this is my LinkedIn. We can connect over LinkedIn. And if you have any questions, then we can probably take questions. If no questions, I think we can wrap up. We have a question there.